Hi everyone, welcome to the first lecture of Digital Signal Processing course. So in this lecture we are going to see what is digital signal processing, what is the need for digital signal processing, what are the applications of digital signal processing. So this lecture, which is the first lecture of the lecture series of this coursework, is going to serve as an introductory lecture for DSP. So let's get started. So when I say digital signal processing, so I have three words in that term: digital signal and processing. So what does the word digital represent? So the digital word represents a type of classification of a signal. So a signal can be classified as either analog or digital. Good. And now the analog signal are continuous signal. So what is continuous, or you may ask what is even signal? So we are going to see what is a continuous signal in, or what even a signal is, in the lecture 2. As far as lecture 1 is concerned, we are only seeing with respect to digital signal processing. So we are going to study only what the definition for our DSP stands for. So as you can see, a signal can be either analog or digital, and an analog signal can be continuous in time, or it can be continuous in another entity like distance, astronomical distance, light year. So they are a distance based continuous signal. Now, a digital signal can be classified as either discrete, which consists of sample points, or numeric. When I say numeric, it can be either binary or octal or hexa. So any signal which is represented using numbers are your numeric signal. So how is it different from discrete? In discrete signals, we use what is called as samples to represent. So a numeric signal is, on more or the other hand, we are talking about a signal inside a calculator or a computer or a mathematically computed signal, whereas a discrete signal is something that is a derivative from a continuous signal. So we'll see more on continuous and discrete in an entire lecture series, and one full lecture will be on dedicated to this continuous and discrete signal. So now that is where your digital place is in digital signal. And now your processing also can work with analog and digital. So when you do a processing on analog signal, you have what we call as an analog signal processing. And then when you have a digital signal, then you do a digital signal processing. So what do you mean processing? Processing is nothing. Processing is just working with signal. I stretch my signal, I shrink my signal, I cut my signal. So all these are processing. So just what you do with your image, you change the size, you cut, you rotate, all those are processing algorithms which will be applied to your signals. Good. So now let's see our next slide, what we are going to see. What are the advantages of DSP? The DSP advantages, there are plenty of advantages for this DSP, especially around the time the computers got invented, because that is when the digital era, that was like the boom. The digital era got just, it got like expanded. The digital era become very popular because there were a lot of areas where computing became, as a problem solver, because what was taking a bulk of space and a lot of processing power was being able to, all were being, can be done on a computer with much smaller compact PCs and also less processing power. The entire computers run on just 10 to 15 volts, whereas your household supply voltage is 230 volt. So you just imagine how much power you are saving when you are thinking about a big industrial manufacturing unit. A computer can do a lot of calculations simple. Only thing is now the interface. So the advantages I have mentioned here are computing power, accuracy, faster, it is reliable, it is power efficient, it is much more compact compared to the analog counterpart, and it is easily scalable. So you want to make this big, you want to make this small, you want to make it expanded to different remote places, all can be done with the help of advantages of DSP. Now coming to a distinctive feature is when the thing is everything was analog before the DSP came into the picture. So now we have to use your DSP. So we have to use the DSP in the midst of your analog systems, because everything has been an analog, and even most of the signals that we get in real time, or most of the signals that are produced in real time, are also analog in nature. So what happens is the place of the DSP is always inside an analog system. So the distinctive feature of this is it is possible for this to happen given we have a proper interface with analog. So the DSP has to be interfaced or integrated properly with the analog unit, and this is normally possible with the help of what we call as analog to digital converter and digital to analog converter. So we'll be seeing it in the coming series. So we are going to see two examples here. I wanted to just mention that also here. One is regarding a mobile audio. So you are having a mobile phone and your mobile audio is used, and then the next one is you are using a smartwatch. Good. And both these devices are using DSP and analog systems. Now, in this, we will see now how the analog and DSP go or get integrated or work seamlessly together in most of the systems. So let us say I have a microphone. So I am speaking, right, as we do this class, I am speaking on my mic or my microphone, and my microphone is having an analog audio. The voice that microphone is recording is in analog, is an analog signal, and this analog signal is converted into a digital signal. So the analog to digital is what helps us to do this, the details of which will be also discussed later on. Now the ADC will give you a digital signal, and that digital signal is sent to your DSP processor. So the mic records the voice, my voice, and that voice has been processed for enhancement. So what I did was I did three effects on my voice, which was one is to equalize it, the other one is to noise compress it, and the third one is to amplify it. So I did equalization, noise compression, or noise suppression. It's just getting rid of some of the noises, and then amplification. The amplification is to boost the volume, so it's my voice is very crystal clear to you. So these three processing I did on my microphone sound, and I did all these three using a computer software. So the audio file was processed inside a computer, meaning it was processed as your digital file. And then after I process it, now I'm sending it to a speaker to be broadcast. So I convert it back to analog because your speaker is again an analog device. So this digital to analog conversion, or the DAC, helps us in taking the processed, enhanced, very good quality sound of mine and convert it into analog, which is the same sound, but just it is in analog form, and then it sends it to the speaker where you hear this video. Good. So this is your pipeline, and the base, see, if you see, there is always an analog component. The DSP is in the midst of two analog to digital and digital to analog. And then, but it is working seamlessly together. So this is a very important feature of DSP. And one might say this can also be a little bit disadvantages because every time you need a ADC and a DAC, but it is still it's compared to the other advantages like computing power, computing speed. This is this can be overseen as a disadvantage. Good. So this cannot come as a major disadvantage given the other many advantages that DSP offers to us. So this is what is important to be known, and this is an interview question. So in many interviews they have asked, is DSP used in analog systems, or can DSP be used in analog systems? And most of the time the students say, no, DSP is a digital system. The DSP cannot be used in analog system. DSP can be only used in digital system. But as you can see here, DSPs are always used seamlessly with analog. They can be used on digital also, but that is not the only place where they are used, as most of the real-time signals are analog in nature. Good. Now, next we are going to see what are some of the applications of DSP. So the DSP application examples, if we want to take into consideration, we have many. We have like plenty of applications you can find in books, you can find in web, you can find it in programming these things platforms. So but as far as today's class go, this intro class, I'm going to introduce to you two main applications that I think would be very interesting for a minor project or even for your major project. I'm going to introduce you to one which is a mobile audio processing. So everyone is having a mobile device these days, and what happens is when you call a friend or when you call someone on your mobile phone, your voice is recorded by the mic. Good. So there is a microphone there, and then it goes through the same process where your microphone converts it and it sends it. And then when you are listening to someone, what happens is the RF antenna. So we are putting the receiving end here, receives your input signal. So receives the voice of your friend, and then it processes it inside in a DSP processor. Every phone, you have a Samsung, you have a Nokia, you have Motorola, you have Oppo, any given brand on the market is always having a DSP DIP processor. So what is a DSP DIP processor is? It is a digital signal processing and digital image processing, because you take a lot of selfies on your phone and you talk to a lot of people on your phone. So the voice has to be very clear, and that voice is made enhanced digitally by your digital signal processing. They may have the same filter I'm using right now for this audio. So they may have an equalizer, they may have auto equalizer, auto compressor, auto noise suppressor, and an amplifier, so that your voice is boosted or given sufficient energy so that it is very audible to you. Good. So these are some of the processing tasks that are present in the DSP processor. And you have an image processor also that works with the camera photos. So the photos that you click appear very nice on the camera because there is always a digital processing, a post processing done by a DIP processor. So what is the difference between a DSP and a DIP is the DSP is just a one-dimensional version, and a DIP is a 2D version. So we will cover that in the coming classes. So just to remember, the DSP and the DIP, image processing and signal processing, are very closely related. Most of the algorithms that are applied to DSP can also be applied to your DIP. Now, coming to the next application is your smartwatch. Nowadays, we are not going with analog. The Rolex is going out of business zone. All the major watch companies that were producing analog watch and even digital watch to a certain extent, they are running out of business because now everyone is want an iWatch. Everybody is going for a smartwatch which is able to show you the time. At the same time, it's able to do a lot other feature tasks, which one of which is your health monitoring. So the health monitoring is done with the help of a sensor called as a biosensor. In particular smartwatches, they use something called as a PPG sensor, that is photoplethysmography sensor, or a bio. Like there are plenty of sensors that can go. One of the sensor that I can tell you is it's called a PPG sensor, but they are in general they are all called as biosensors. And these biosensors can monitor your heart rate, blood pressure, activity level monitoring, and these are all digital signal processing. And this processed data is sent to your mobile phone, and you can see for your information. Good. So the two applications that we have seen is the mobile telephony, audio, and your smartwatch. That is very useful, I would say, in this. And you can yourself browse for plenty of other applications. It is used in video processing. It is used in your television. It is used in your cell phone cameras. Right? In your cell phone cameras, the DSPs are used mostly if you record a video with an audio. Right? If you have an image with an audio, then definitely you have a DSP working there. So now we are going to see this ADC DSP to DAC. So what is this analog to digital? So we're going to see briefly. You might have seen this already in previous classes. So since it's an intro lecture, we are going to see a little bit on these things, and before we get into the depth of DSP in the coming classes. So the analog to digital is also considered as it's a pre-process. It's a prior happening to DSP. It happens before you enter the DSP block. So let us say this is my analog signal, a sine wave, and now I have a process called as sampling. Right, the sampling is a process, and what it does is the sampling is going to select certain points. So through sampling in a continuous signal, when I send a continuous analog signal through a sampling block, the sampling will select points at definite intervals. So at where, at how, so this is defined by what is called sampling rate. So I just tell them you select 3 samples in one peak. Right, in one cycle you select 3 samples, and that is what you see here. So you see there are 3 samples in one cycle. So that is my setting. So if I set it as 6 samples in one cycle, then my sampling algorithm will select 6 points. If I put it as 10, then it will select as 10. It will just do what I say. So the setting is just in the top of the program. As we will be seeing, we have to just give the number of sample points in one cycle, and that is how it will be selected. And now after sampling, what we do is we keep only the points. So we get rid of see now the analog signal is not there, and we have only the points, and these points are your digital signal. So these points alone, so you see here the sample points alone constitute your digital signal. So we are talking only these points, and now these points are processed. So let us say I do something with this, and then these dotted lines represent. So the dotted lines that I'm drawing represents your digital to analog conversion. These dotted lines represent your digital to analog conversion. So you see your output signal after DAC looks almost close to your analog signal. Understood? So we take a continuous analog signal, we sample it, then after sampling we get only those red points, or the sampled points they are called, and I process and then these sampled points is where the DSP comes in. So we send these point coordinates, we send the points value, each point represents a particular value, right, and this is sent into your DSP. And the DSP applies some computation algorithm to these points, and then it sends these points, it processes it, and it comes as an output of the DSP, and then these points are joined together, and that is your DAC. So you see the dotted lines represents DAC. So in this case, I'm going to say that my DSP is just a unity filter. It's an unity all pass filter. So it means it's just like your exams during this time. So it's like an unity all pass filter. So it is passing all the points. It's not getting rid of any points. It's not altering any points. So it's a unity all pass filter. And now after the processing, after the DSP, I join these points using this dashed lines, and that is my DAC. So it's clearly written here. The ADC is where it consists of only the red points, and your DAC consists of the dashed lines from only the red dots. Good. Nice. So that is about your ADC, DSP and DAC. So we are going to see a plenty of things. This is just like the very at intro level. We have seen what sampling is and what is doing. We are going to see in depth on sampling. So in the in this, as we go along this course, we are going to see a lot more of this sampling, a lot mathematical derivation of sampling, and some numericals or some mathematical examples of sampling. Now, just to make things clear, because this is like the core foundation for DSP, I wanted to write another example with the sine wave. So what we are going to do is, I am going to take these are the value. I have plus ones, the max values, and the minimum values are the minus one. And when I do sampling, so when I say sampling or it is an ADC process, I am going to get a array or a matrix which is going to have only these values. Got it? And now this is my digital signal. So what is shown within the bracket, 1 minus 1, 1 minus 1, etc., that is your digital signal. And this digital signal is now, it's sent, or it can be stored in a computer. Good. It can be processed in a computer. So let us say that is your audio signal, that is a music. It can be saved as an MP3. It can be stored in the computer. It can be played with the player. It can be done anything. So now if I want to send this to, as long as it is in the computer, it can be done in the analog. It can be stored in the digital form. And now if I want to send it out of the computer, so I want to send it back, then what I do is, this is right, this has to be done is DAC. So my DAC is joining these points. So I will be joining the points, and then I will be getting the analog signal back. So this illustration also should clear you the whole process of ADC to DAC, and where your computer comes into the picture. Because that computers, when I say computer, it can be a computing machinery. So DSP algorithms are digital signal processing algorithms, and that happens on a digital processing unit, right? Which is your CPU, or it can be a GPU, or it can be any of a computing machinery processing. So this is another illustration of your analog plus DSP. Or when I say analog plus DSP, we are talking about ADC, DSP, and DAC. So I told you what is an unity all pass filter in the previous class. So it's going to send all these samples unaffected. So it's probably not doing anything, and we still have that filter because it can be used at certain places to just keep all the values. Now we are going to see what are the limitations. By now you have seen a lot of advantages, a lot of stuffs on the significance of DSP, why DSP is needed, everything on the positive sides of things. But why do we have a problem, or where is the limitation when you talk about analog plus DSP? The limitation is your analog signal is typically extending from minus infinity to plus infinity. When I say you have an analog signal, it generally means it is a continuous signal extending from minus infinity to plus infinity. And as you all know, our computers can't do infinity calculations. Computers are finite number calculators. So you cannot process data which is extending from minus infinity to plus infinity on your computer. So you have to approximate your analog signal, and there lies your limitation. So when you approximate something, so when you do some approximation on anything, when you do approximation on anything, you are missing out on quality. So some of the qualities of that signal will get truncated or will get eliminated. So how? So let us say a digital signal is a finite duration signal. So a signal which is existing in this band, that is your digital signal, and this can be processed and handled easily in your computer or a digital signal processing. Now the when I do my analog to digital conversion, basically what I am doing is I am taking this minus infinity to plus infinity signal and I am representing it in this small band. So when I do that, when I am representing when I am doing this approximating of representing a minus infinity to infinity into a smaller band with a lower limit and upper limit as a finite number, I am approximating the signal, and when I do approximate, I'm getting rid of a lot of information on both sides, right? That's what, if you have to logically think of it, I'm getting rid of many information which on the other side, on this side of the lower limit, on the left side of the lower limit, on the right side of the upper limit, and this could definitely lead to some quality degradation, right? Analog is, so that is why people used to say like gramophone, it's like so much, we need analog sound systems rather than your digital sound systems, because it cannot match the analog device. But on the other hand, the analog signals or the analog systems are subject to the wear and tear over a period of time. So that wear and tear will definitely hamper the quality of the analog audios or analog signals, whereas the digital sound that we are storing in the computer is having infinite life. So the lifespan of a digital signal is infinity, whereas the analog signals or analog systems lifespan is very finite. For instance, if you take any analog device like a fan or a speaker, after a certain time the sensitivity of the speakers or the mics or the fan rotations will go down. That is the wear and tear of the machineries, right? So so what we can summarize from this lecture or from this slide is the range conversion, which is from minus infinity to infinity to a smaller finite range, will lead to quality degradation. But also the digital don't suffer the wear and tear as compared to the analog. So which means the digital signals are still okay for a longer period of time compared to analog. So right, preserving the data, preserving the signals is better in analog, better in digital compared to analog. Now we are going to see something about the x-axis of DSP, right? So that x-axis is always time. So as we have seen on the first page, what I would say is whenever you have an analog signal which is continuous in time, they are called as continuous time signals. So we are going to introduce here a little bit about continuous time signal and discrete time signal. So in the rest of the lectures that will follow in this course work, we are going to be dealing with mostly continuous signals and discrete signals. For the majority of the lectures, mostly on discrete signals, because this is digital signal processing. So the Oppenheim and Schaeffer's book says that discrete time signal processing, which is a very, very accurate writing. So we are calling it as digital signal processing, but the most apt name for this subject should be discrete time signal processing. Okay, so that is what. So let us see first what is a continuous time signal. A signal which is continuous in time domain. So the time domain means your x-axis is always time. The y-axis can be anything. It can be amplitude, it can be energy, it can be torque, it can be any other parameter. But the x-axis is always time, and the signal is analog in nature. Then you would call it as a continuous time signal. In DSP, you see anytime you hear the word signal, or you see analog signal, then we are talking about CT signals. We are talking about only continuous time signals. Digital signals, on the other hand, in DSP are the time sampled signal. So we saw what is sampling. When I say sampling, it is ADC, analog to digital conversion. And the time sampled version of your CT signal, your continuous time signal, is your discrete time signal. So this subject, digital signal processing, is in fact discrete signal processing or discrete time signal processing. Understood? So we are gonna see a lot of discrete time signals, how they are how they are processed, how they are computed, how they are represented, how they are plotted. Plenty of things on discrete time signals. So from here onwards, whenever you see analog signal in this course, we are talking about CT signal, and whenever I say digital signal, or when I write digital signal, then I am writing what I am talking about is a discrete time signal. Whatever I am good. So the representation, that we'll just write two equations today, because no, so far DSP without equation feels totally incomplete. So I'm going to write just two equations for today's class. One of the first one is integral minus infinity to plus infinity x of t dt. That is your CT signal, CT mathematics. Then your discrete time signal is sigma n equal to 0 to n minus 1 x of n. So where the n represents the sample point and capital N represents the number of samples. The small n represents the sample point and the capital N represents the number of samples. Good. So I guess that's enough for the introductory class today. We will see, we'll just summarize what we have seen today, the lecture 1 summary. So what are the things we have seen? So let me list down. The first thing we saw was introduction to DSP, right? What is an analog signal, or what is DSP in general? Signal classification, analog, digital, continuous, discrete. Good. Applications of DSP, we have seen mobile, audio, smartwatch, two big things. I also suggest students to take up projects on one of these, because you have a minor project. So you can select some state of the art algorithm. I would always welcome a sound filter. So you take a voice and you can introduce some effect into your sound by adding some filtering options or designing a filter. That is one project I would ask you to do. And another signal is you can work with the PPG and obtain heart rate, BP, blood pressure, and etc. vitals, bio vitals. That would be another good idea for a project, but I leave it up to you. You will have a mini project. I will be coming to that later on. So we have seen about ADC, DAC. We have seen sampling at very intro level, and then we have seen how CT and what are CT and continuous time and discrete time signals and how they are represented. See you for lecture 2. Thanks.